Right, good evening and welcome to today's class. Thank you very much for making time to attend. Last time we had a discussion of, or rather we did a review of 2601 related content. We looked at regular expressions and finite automata, and I hope the examples were enough for you to refamiliarize yourself with those discussions again, right? So now today we're going to start with the investigation, or we're going to start looking into what are called context-free grammar. But at the end of last class, we said regular languages were not enough, and we demonstrated why they were not enough, because they could not keep count, right? So the way specific or languages that require specificity, right, did not suffice as regular languages, right? So now let's look at how that changes in context-free grammar. Right. So what is it that we're talking about? A context-free grammar is a collection of three things, right? An alphabet of letters called terminals, which we are going to make strings that make the words of the language. So the alphabet Y is the one that is used to make up all the words in the language. Then number two, a set of symbols called non-terminals, one of which is the symbol S standing for start here. So we have a set of symbols called non-terminals. So far we now have terminals and we have non-terminals. Right. And then a finite set of productions of the form non-terminal goes to a finite string of terminals or non-terminals. Right. So what we have is we have a set of terminals, then we can have a set, let's call this a set of symbols called non-terminals represented by capital letters X, Y, right, for example. And then part three, we have a set of productions. So what are productions? Productions are just rules used to form words in the language. Right, so what they're saying is if finite set of productions in the form of one non-terminal, so you can pick anyone, one non-terminal goes to a finite string of terminals. You can have, for example, A, B, A, or you can have A going to A, X, B, or you can be A going to X, Y, Z, whatever. So all I'm trying to do is to show that the productions can take any of these three forms. It can have a non-terminal going to terminals only, a mixture of terminals and non-terminals, or non-terminals only. All these three suffice to be productions of or to be called productions. Right, I think before I proceed, I have to ask something of you. I haven't received the assignment questions. Right? I understand they're not in the study guides or tutorial letters. If you have them, could you please send them through to my email so that I can we can have a look at them as well as we do the classes in the content. Right, thank you. So that is the definition of a context-free grammar. Now let's look at a context-free language now. Right, so the language generated by context-free grammar, right, is a set of all strings of terminals that can be produced from this start symbol S. So we said these are productions, and there is a wording there that says S stands for start here. Right. So all productions or all words need to originate from S. So S replaces the initial state from finite automata. In finite automata, with the initial state, here we have the non-terminal S signifying start here. Right. So all words need to find its origins or its roots from S. If you have got a context-free grammar and your word cannot be tracked back to S, then it is not a word in the language. Right, we're going to look into that in more detail. So we say that if that can be produced from the start symbol S using the productions as substitutions, right? A language generated by CFG is called a context-free language. So context-free grammar begets a context-free language, in a nutshell. So we have an example of a context-free grammar here, right? So we've got, and this is now notation difference, right? So S goes to AA, S goes to BX, S goes to AXX, X goes to AB, X goes to B. So these two are equal, right? They are one and the same thing, these two CFGs. Right, so now what we're saying is if we've got a non-terminal, right, appearing more than once on the left-hand side, right, we can rewrite it in terms of this format to say S goes to this one, or, which is this line over here, or this or that. Right. And then likewise, X goes to AB and X goes to B can then be written like that. So that is just notation. Now, looking at this, right? If we wanted to generate words from this, how would we do it? How would we generate words from this? So you pick a starting point, right? So S goes to AA. So now when we use this symbol, we are now deriving, right? We can substitute, we've substituted S with AA, right? Because these are all terminals, it means that AA is an element of the language, right? We can choose to have, we can start from S goes to BX, right? This is not a word in the language because words in the language consist only of terminals. Words in the language consist only of terminals. So if you still have a non-terminal as part of your derivation, then you have not reached a word in the language. So we now need to substitute X, so B. So we can either choose from here or from there. If we choose X to go to AB, then BAB becomes a word in the language. Or we could have S to BX goes to BB. Therefore, BB becomes a word in the language. Or we can also have AXX, right? X can go to, the first X can maybe go to AB, and then the second X can go to A, B, like that. Then we can have A, B, B as an element of the language. Right. I hope we see how we derive words from a context-free grammar and how we can manipulate the given productions to generate a word that we want to generate. Any questions so far? No? Okay, good. Right. So we're going to look at more CFGs, right? Let's proceed with a little bit of theory. Then we'll look at more CFGs and attempt questions. So for a given CFG, right, we have got productions, right? And if our productions are of the form, say X goes to, right, or this can be different non-terminal, intersect, right. If all the productions have the following property, you have got terminals, and then at the very end, you've got a non-terminal. Right? You've got terminals, at the end, you've got a non-terminal. Right? As long as you have exactly one non-terminal at the very end of a production. We call these semi-words, right? So here we're saying for a CFG, a semi-word is a string of terminals, maybe none, concatenated exactly with one non-terminal on the right. So we have terminal, 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 non-terminal, like we did here, like we did it, right? Or maybe non-terminals, like we showed here. If we have this kind of scenario, we say that this is a semi-word. This is a semi-word. Now, let's look at this theorem, which is important. Right, all regular languages can be generated by CFGs. Right, all regular languages are context-free languages. So, mathematically speaking, we're saying regular languages are a subset of context-free languages. Right, it is not the same to say all context-free languages are regular languages. No, all regular languages are a subset of, or regular languages are a subset of context-free languages. Right. So now, how do we know that the following language is a regular language? How do we know that the following language is a regular language? Right, so it says if all the productions in a given context-free grammar fit one of the two forms, right? Number one, a non-terminal goes to a semi-word. We defined what a semi-word is, right? Or a non-terminal goes to a word, or rather a string of terminals, where now may be also be in the string. So if we have a semi-word or terminals only, then we know that if all the productions are semi-words and terminals only, we know that the CFG represents a regular language. Right? We know that it represents a regular language. Okay. So if we consider this CFG, right, we have a semi-word, 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 okay? This is supposed to be now, sorry. Semi-word, semi-word, word, right? Therefore, this is a regular language. If it is a regular language, it needs to have a regular expression and it can have a finite automata. So if we wanted to demonstrate the regular expression for this language, the way to do it is first we convert it to, we draw a finite automata for it, then number two, we generate the regular expression. Right, to generate a finite automata for it is quite simple. Right, we can start with the transition graph, right? We can either generate a transition graph or a finite automata. If you wanted to draw a finite transition graph, let's start with transition graph first. It says here from S, each state in the finite automata is labeled by a non-terminal, represents a non-terminal. So here it says with an AA, go back to S, and with a BB, go back to S. And it accepts now also the initial state is also a final state. Okay? And then the regular expression then becomes, we are saying it's AA or BB clean star. Right. So this becomes the language. If we wanted to draw the finite automata, we can then say from S, we have an A, right? And then we come back with an A. And then we have got a B, and then we come back with a B. So this is S, initial and final state, right? Which means here with an A, with a B, go to a looping state. B, A. This is non-final, we have only one final state, which is that. So this becomes the finite automata for this, leading to the same regular expression. Right. So That is the language. Now you can describe this language. This will be the language 1. Even letter words. Right. Where A exists, where A's exist, they occur in multiples of 2. And where B's exist, they also occur in multiples of 2. Where B's exist, they also occur in multiples of 2. So if we combine this, we get the language described here. All right. Any questions? Cool. Let's move forward. We're given another one. We can draw. We need to draw the FA, right, or transition graph. We need to give the regular expression. So if we start here, initial state, which is our S, right, with an A or B, we're staying here, right? With an AB or BA, we're going to state X. But this is also a final state because now it's accepted. Right? If you are in X with an AA or BB, you stay here. And then with an AB or BA, you go back there. Right. Because X does not terminate, it does not have a terminal, it means that it is not a final state. A final state terminates with a terminal. Right? So the regular expression becomes AA or BB. Okay. Then we have got AB or BA. Okay. So we can have this. You can have AA or BB, and then we have AB, AB or BA. Right. So and then once we have this, we can have this as many times, and then we can loop this, I think. We can loop it. Let's write it down. Let's use Kleen's theorem. Let's be clever about it. So we go there with AB or BA. And then once we get there, we've got AA or BB, Kleen closure. And then we've got AB or BA. Okay. And this itself, in itself, is a loop. This is a loop in itself, right? And that is a loop in itself as well. So if this is a loop, we're going to put a Kleen closure there, okay? But then at the end, we just need to say, after we come back to, let me just say this, after we come back here, we can have AA or BB Kleen closure. So this is a loop that we can go into, or we can have A or B. Sorry, A or B. And we can choose not to do this part. But if we choose to do this part, then we can continue doing that like that. So this becomes our regular expression. All right. Now, let's go on to tree diagrams, right? We say a context free grammar is called ambiguous if for at least one word in the language that it generates, there are two possible derivations for the word that correspond to different syntax trees. Syntax trees. Right. What is a syntax tree? So we have got what we call a tree diagram. So it shows the derivation of the word. Say we've got a production, a CFG, ASB, AB, like that. Right. If we wanted to see whether the word AB, in fact, B can be generated by this language, we draw a tree diagram. The root or the root node becomes S, right? And then we say S breaks down, right? Our word starts with an A, so we've got a production starting with an A. We've got it goes to A, it goes to S, and it goes to B. Then these are terminals, they are fine. The non-terminal breaks down again. We can have A, S, B. Again, here this can break down. We have got A, S, B. And then lastly, we can then have A, B. So here we're now using this production. So if we move from left to right, we're going to have A, B. So a tree diagram, we are saying that root node is S, then leaf nodes are terminals such that when we pass from left to right, we get a word in the language. We have a word in the language. All right. So that is a tree diagram. Now, when we talk of ambiguity, we say a language is ambiguous if there is more than one tree diagram for such a word. When there is more than one tree diagram for a word, for one word in the language, then we say the language is ambiguous. Okay. Now, this is what is called a tree diagram. It is specific to a word. Tree diagrams are specific to a word. Right. Now, the next thing we have is what is called a total tree diagram. So how is it different from a tree diagram? Okay. Represents all words in a language, the whole language. What do I mean by representing the whole language? All words are found on total tree diagram. All right. So that is the major difference between tree diagrams and total tree diagrams. So in our previous example where we had S goes to A, S, B, A, B, okay, the total tree diagram for this would look like this. So we've got S, right? The nodes will be the different productions, okay? So we're going to have A, S, B, then we're going to have A, B. This terminates with the word A, B is part of the language. And then this one has got a non-terminal. We're going to have A, right? S is replaced by A, S, B, B, and then here S is replaced by A, B, B. This is terminated, this is terminated. You continue. This is going to expand. A, S is replaced by A, S, B. Then we've got these two B's, and here we've got A, S is replaced by A, B, and then we've got these two B's. You continue expanding like that. So you see that this is a word in the language, word in the language, word in the language. If we expanded one more, we'd have A, B, 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 a word in the language that we tested before. So a total tree diagram will give all the words in a language. So this stretches to infinity because we see that we can generate A to the power of 100, B to the power of 100, A to the power of 1 million, B to the power of 1 million. So it can stretch to infinity. Right, so that is a total tree diagram. Right, cool. So now let's look at some questions. Right. So these are typical assignment questions. They extract them from the textbook. So I've done the same, not knowing exactly what the assignment questions are. So I'll be waiting for you to send those. Okay. For the following CFGs, find the regular expression that define the same language and describe the language. So are all the productions in the format of semi-words and terminals? Yes. Right. So then let's draw the find the regular expression. So to find the regular expression, don't necessarily find it automatically. You can just draw transition graph. So we've got S, right, which is an initial state and the final state. With an A, it goes to right. So if you see that they've been emailed to me, so I'm gonna look at them. I'm not gonna have time to put them up for the class today, but maybe we're gonna start with them next time that we meet. Okay. Thank you very much. AB. Right, with a B, you go to A. Right, with an A, you go to, if you are in A, with an A, you go to S. With a B, you go to S. The B side. And then that's it. So the language that we have is, we can have AB or BA like that. So this is the language that we have. This is the language that we have. So in this language, we can never have language of all even letter words. Right. Language of all even letter words, that's the first one that we see. Of the even letter words, right? Neither start with an AA or end with an AA. That do not start or end with a double letter. they do not start or end with a double letter. Okay? Or even letter words that do not start or end with a double letter. Right? The other restriction that I can see is that clumps of A's or B's contain at most two. At most two elements. So what I'm saying is each clump, if we have a clump of A's, it's not possible to have more than two A's, right? It's possible to have two A's, but you cannot have more than two A's. To have two A's, you can have BA, AB, okay? So you can have that, but you cannot have another A anywhere else. So this combination of these two gives us the description of the language. All right. Next one. S goes to BS and so forth. So we've got semi-words, terminals. All right, let's draw the transition graph for this. Here we can do a finite automata, it's fine. Initial state S, it is not a final state. With an A, you go to X. With a B, you stay here. And then if you're an X with a B, you go to S. With an A, you go to Y. Right? If you're in Y with an A or a B, you stay. With an A or a B, you stay there. And you can terminate. Okay? It terminates like that. It terminates like that. So once we do this, we can then now find the regular expression for that. This is the final state. We have B clean star A, then we can have B clean star A, then you can have A, then you can have A or B clean star. Right? So it's a language of all words with at least language of all words with at least two B's, all words with at least two A's, with at least two A's, okay, and one B, two A's and a B between the A's. Like that. Right. So that's the solution there. Let's look at another one. Right. We are given a CFG and they ask what is the language this CFG generates. So here they're asking us to interpret the CFG. Now, this is not a regular language. We do not have a same word. Right? This is not a same word. But what this, if we read from S, what it tells us is our language are going to take a specific format. Our language is going to take a specific format. To say you need to have at least two A's, all right? At least two A's. And then we need to understand what X is. Right, so X goes to AX or BX or now, right? So in short, we are saying you can have AX, BX now, then here you can have AX, A, bx, or A with the now. We can continue like that. We can have AA, AX, AA, BX, A. Now we can see what's happening here. It can generate any substring. So literally speaking, if this was starting from S, for example, this semi-weight terminal, right, would have in this going to an A or a B going there, and it's a final state like that. So this is equivalent saying A or B string star. So this generates the language of all words over the alphabet A, B, right? So here we are saying S gives us a guideline of what we are requiring. We want words with at least 2 A's, and then so typically we are saying we have got A or B, clean star, A or B, clean star, A or B, clean star. Right? So that is what we are saying. If you are saying this, then it's all words with at least 2 A's. So this is a suffice, this definition will suffice. Right. So if you go to chapter 13, chapter 12, right, you see examples of these small CFGs that have been interpreted that make up the bigger CFGs. All right. Right, what language is generated here? So we've got all words starting with an A, right? Or all words with a BAA in them. Words starting A or have an BAA substring. Right, so that's the first part that is described by these two productions. Now, if we go to X, how does X behave? X goes to XA, XB, or now. Right, so what you see is that this suffices because X eventually terminates with a now, so it goes to A or B. So as long as you have described these two over here, then this is fine, right? We're starting with an A or have a BAA substring. This should be fine because XA is only replaced by now. XB, X can be replaced by now, X can be replaced by now there, meaning that we can retain A or B everywhere that we want. Right. So that is the language that we are trying to describe. And then they say find a word in this language that can be generated in substantially 2 different ways. So we want to have 2 different tree diagrams, right? So let's find A, B, A, A. Okay. So let's start with saying S. We go to X, B, A, X, right? And then this X goes to XA, this stay, and this X goes to now. And then once we do that, this was supposed to say X goes to X, and then goes to A, and this X goes to now. So if you move from left to right, we've got A, B, A. And then we can produce this in another way. We can say S goes to A, X, and then X goes to X A, then we can have X goes to X A, then X goes to X B, then this X goes to now. Then when we pass it, we're going to have A now B A, which is equivalent to AB A. So these are different ways that this word can be generated. So this language is ambiguous. All right. Then lastly, there's a question in the textbook. It should be part of the assignment as well. They give you, and there's a common mistake that is made when attempting this question, right? You are given a word. So on the left, there's a list of words. On the right, there's a list of CFGs. So the question says, right, for each word, check whether it is accepted by each CFG. Right? If it is accepted, draw a tree diagram for it. So you're supposed to check the given word on all the given CFGs. Right? For example, if we're checking on the word CFG1, right, with ABAB, with CFG1, can we generate ABAB? Right? ABAB cannot be generated, right? No, ABAB cannot be generated. Why? You see that we have got this expands with ASB, ASB. So it's language A to the power of N, B to the power of N, and ABAB is not that. Let's go to CFG2. CFG2 says ASBSA. We want ABAB. Right. This says S terminates with an A. So this represents all the words ending with an A. No, since CFG2 represents words ending with an A. Words ending A. All right. Then check CFG3. Right. If we look at CFG3, ASB, this we are not interested in. Right. Or maybe we are. Let's hold on for a minute. ASBX, right? X can go to AXAA. So if S goes to X directly, then it goes to words starting with an A, ending with an A. We do not want that. So we need to focus on that. But we see that AS and ASB, right? We want starting with an A, so we have got S goes to A. This can be S, this can be B, right? And then we now need another. We need a BA in between here, right? So, but then S can only go to A or ASB, meaning that this word cannot be generated. So you also say no, it cannot be generated. No, it cannot be generated. Okay. Then CFG4 says we want to check whether ABAB is generated here. AAS, right? S ends with an A, right? So all the words end with an A there. All the words end with an A, therefore the answer is no. And then if you look at CFG5, we've got A, B, O, BA. Our word starts with an CFG5. Our word starts with an A, so we need to start with S goes to A, B. Then B goes to BS or ABB, we need to have B and then go back to S, right? Then S can now be AB again. S can now be A, B, and then B can go to B. So the answer here is yes, and we give the tree diagram like that. All right. So that is it for chapter 12 and chapter 13, and we are only left with one aspect of chapter 13 that we're going to look at in the next class. Any questions? Right. Thank you very much for attending. We meet again on Tuesday, same time. Enjoy the rest of your evening and the rest of your weekend. Goodbye. Good night.